And Wilson, thank you for inviting me for this in the conference. Yeah, my talk is about metaphoric model of the notion of emergence and notion of life. And metaphoric life model, there was some ancient rock garden in Kyoto, ancient temple. And rock garden can reveal cosmos, time, evolution, etc. And then my model is. And I think life is always a get with the notion of emergence. The notion of emergence is defined by using boundary between hierarchical levels, microscopic and macroscopic levels. And if this kind of indefinite boundary, uncontrolled indefinite boundary is implemented in laboratories or automata, it reveals classical behavior. We call it hierarchical classical system. This is the first network model. And if this kind of independent boundary is implemented in the sample paradox, it will result in homeopath stability system. And this is another network model. Now, first of all, we start from the statement said by Stephen Wolfram. On just one seed, as computation proceeds by applying rule 30, the elements accelerometer rule to an initial condition, a complex pattern emerges. Then he says only a computation proceeds, complex pattern emerges. But there is a double standard behind in the statement. Initial condition is regarded as one seed in vacant space on one hand. It allows the notion of emergence. And on the other hand, an initial condition is regarded as boundary sequence 001, 00, and something like that. It allows that a rule 30 can be applied to an initial condition. Therefore, in the macroscopic point of view, emergence of complexity we have. And by contrast, in the microscopic point of view, there is just a computation process. There is a double meaning and a double standards. And it sounds as if emergence was just an illusion. The question arises, emergence is just an illusion or not? And to my issue, my answer is the following. We have to accept double standards. And indeed, we introduce indefinite and controllable boundary between double standards. In this sense, we cannot determine or verify whether an observer stands at a microscopic or macroscopic level. Therefore, we cannot prove or we cannot verify that emergence is just an illusion. The notion of emergence can be championed paradoxically. Therefore, my answer to the issue of emergence. And this idea is applied to the sample paradox. Sample paradox is the following. Taking one sample grain from a sample, leaves a sample, and this process is perpetually repeated. It results in the paradox that one just grain is a sample. And in this framework, there is a basic assumption. Any concept is defined by a pair of type and token, and the type and token, there is no inconsistency between type and token. And for a concept of sample, type is a property of the sample, and the token is aggregation of the sample. And in general, a type reveals intent and general property and something like that. And token, in general, reveals object reference and example and something like that. And we believe there is no inconsistency, no conflict between type and token. Therefore, this the concept of the sample is isolated from any other concept. Therefore, standard grain is separate, independently separate from sample, and they are not mixed with each other. But Actually, in talking about type and token, probably some contamination between type and token objects. And this contamination triggers the shift or modify the consequence. Therefore, it allows the transition from some part to some grain or some grain to some part, something like that, evolution. And now, this idea is applied to the throughout multi-passage model. First, the type as a bonus, some part, is expressed as muscle structure as an initial condition. This muscle structure is set in the space at first. And application of some grain, that is a token of the constant some file, is expressed as some operation. First, we pick up some vacant space adjacent of the some file, and adjacent some grain of the space is swapped with each other. And this swapping is perpetually proceeds to keep the some file as a whole. As a result, this vacant space is devoted, embedded in the operation of the aggregation of this aggregate. And if this operation succeeds, the system moves perpetually. But actually, this process, this integration fails, and this system destroys. Therefore, a little bit device is modified by the following. First, some vacant space is chosen, and the adjacent some grain is chosen. And the swapping of the some grain and the adjacent vacant space is swapped perpetually proceeds where this swapping avoids its own trajectory, something like that. This avoidance stabilizes some power as a whole. In this scheme, we can see a double rule in this, and separation between some power and aggregation of some grain. And this is an XO circle. And in the circle, we can see the self-reference between a grain and the grain parts, that is a trajectory of the grain movement. And therefore, it is a macroscopic and microscopic perspective, and in the circle reveals indefinite boundary between them. And this is a simulating result of the moving somehow. This moving somehow obviously eats vacant space and abandons it. And this only this movement modify this, the shape and move this system. And if this system expands to a huge space, there was some whose sources distributed, and the vacant space is generated at each whose sources, and they are transported in the system and abandoned to external space. And this iteration is a basic operation of the moving somehow, and it results in the adaptive network connecting all resource alignments. And this network is adapted to some extent, but some groups remain different. This network is robust for the perturbation to some extent. And actually, we compare the simple stochastic model of network system. And the network generating simple stochastic system. In this system, there is a trade-off between edge per node and minimal pass and something like that. But our model and real prism is a giant omega. Weaken this trade-off relationship like this. Therefore, the moving sample mimics our member very well. And we shift to the next methodological model, graph-oriented and hierarchical system. Graph-oriented hierarchical system is meant by implementing intermediate layer in the class 3 system. And given macroscopic perspective featuring order or class 2 pattern, and microscopic perspective featuring disorder or class 3 patterns. Here we introduce intermediate layer balancing competing goal macroscopic and microscopic perspective. And complete recipe to make a hierarchical class form is the following. First, we choose a class 3 one parameter pattern. And we analyze this global behavior by Rafset analysis. The Rafset analysis was proposed by us recently. And so we introduce intermediate layers was a balance desired class 2 behavior and original class 3 behavior. It results in class 3 elements several pattern, except with intermediate layer showing class 2 behavior. First, we explain Rafset analysis. And given map assumption that a close relation can be derived by a map, and members of the set is divided into class classes like this. And from an equivalent class, two approximations are defined given the equivalent classes. And for the subset X, lower approximation for X is defined by a collection of equivalent classes included in X. Therefore, in this case, lower approximation of X is a set C, D, E. And upper approximation of X is defined by a collection of equivalent classes intersected by X. Then, therefore, in this case, upper approximation is a set of all members. And such that X is roughly approximated. That is why we call it a rough set. And when we collect a fixed point with respect to this upper or lower approximation in the form of R star X equal X, lattice is always the Boolean, trivial Boolean lattice, given equivalent class. And these equivalent classes are regarded as atoms of the lattice. And all combinations of the atoms are collected, and they constitute a Boolean lattice. But it's too trivial, but recently we verify any lattice can be obtained by composition of two approximations of different relations. We use different kind of equivalence relation, and we composite these lower and upper approximation, and we define the fixed point with respect to these operations. Actually, given two kinds of maps, that is expression for one-to-many mapping, and we obtain two kinds of equivalent relations, S and R. And due to the mixture of two relations in the form of X or R star X star X, by collecting a fixed point, we obtain a non-Boolean lattice in general like this. And compulsory, given a boundary relation between two kinds of sets, we can reinterpret the two kinds of collection of equivalent classes like this. And we obtain a direct lattice like this. And this lattice analysis is applied to parameters automata to estimate global property. We pick up here rule 90. Parameters automata is defined by a local transition rule for triplet like this. And this local transition rule is applied to the final sequence, and it reveals a time development like this. And here, only one way is depicted by a back pixel. And first, transition of internal triplet and input condition. Therefore, rule 90 is interpreted by the transition of here, internal triplet under 0, 0 input. And due to this transition, all triplets divided into some equivalence classes like this. And this is equivalence classes derived by the first R equivalence relation. And another equivalence relation is can be derived by any of the transitions under 0, 1, 1, 0, 1, 1. And these all triplets are divided into equivalence classes like this. And two kinds of equivalent classes are connected by this relation for rule 90. And this connection is expressed by the binary relation like this. And from this, we correct the fixed point with respect to R star x. Finally, we obtain also complementary lattice like this for rule 90. And this lattice analysis can be applied to all elementary matter, 256 elements of matter. And all of them are estimated with respect to distributivity and complementarity of underlying lattice. And each elementary matter is expressed as a pair of distributivity and complementarity of underlying lattice, and is plotted in the prime of distributivity and complementarity. And we obtain a frequency distribution of group class 1, class 2, class 3, and so on. And this diagram shows all class 1 surround matter with distributed lattice. Class 2 is not distributed in the strict sense, but they show a strong distributivity. And class 3 surround matter show a weak distributivity and strong complementarity. Therefore, roughly speaking, we can divide class 3 from class 1 and 2 with respect to distributivity and complementarity. And therefore, by using lattice analysis, we can estimate global property of the lattice of matter. And we show the recipe to the complete hierarchical classified system here. First, we here pick up class 3 surround matter, rule 146. And this is two kinds of equivalence classes and the connection. And the connection is expressed by binary relation like this. And the underlying lattice is like this. That is non-modular, non-distributed lattice. That's the property, essential property of the class 3 matter. And here, if some elements of the binary relation and the group are removed, the underlying lattice is changed from this to this. That is more distributed lattice. Therefore, if we implant some operation on this element matter, this has a little bit class 2-like behavior we expect. As a result, after this operation, the behavior can develop from this system and change from this to this. Now we show the detail. First, we pick up rule 146, and rule 146 transition is re-expressed with respect to the internal triplet under zero range. And this is a equivalent classes resulted from this transition. And another equivalent process derived by any other transition under the 1, 1, 0, 1, 1. And the connection between two kinds of relationships is expressed like this. And the binary relation derived from this connection is expressed like this. And then underlying lattice is show non-modular, non-distributed lattice. That is a property of class 3 as mentioned before. And if this element of the binary relation is removed, what is that? Now we focus on the row accompanied with a small a. And in in this row, small a, large a, this element means transition this to this. And AC means transition this to this, something like that. And therefore, removal of AA and the small a is the transformation of the transition from small a is to either AC, AD, AE, something like that. Therefore, if removal of these elements, we have to block transition from here. They are replaced by these block diagram or intermediate layer transitions. And yeah, we have to note that these transitions are consistent with rule 146, but they are not consistent with rule 146. Therefore, we here implant some inconsistency of elements. This is a result of the rule 146 driven hierarchical system. It consists of the original rule 146 and block diagram, block transition, or intermediate layer transition like this. And by using some filter, it is easy to see there's some gradient like this. And by following the discussion, Masha Cook and student problem, we can also say this system can emulate a Turing machine by using gradients. And also we refer to vagueness in intermediate layer or block transition. Block transition is from factual binary sequence to triplet sequence. Therefore, it is overlapped. Therefore, dependent on the order of updating, the final result pattern is a chain like this. This is uncontroverted or inconsistency inherited in intermediate layer transition. Now we summarize the recipe. First, we pick up microscopic rules at the zero matter. Rule 1, it's non-distributed, it's non-distributed like this. And we desire a microscopic constraint like this, that feature cluster property. And to balance competing goal, microscopic and macroscopic rule, we introduce intermediate layer transition with vagueness, and it results in hierarchical classical systems. And further, we refer to the converse approach. First, given class 3 all elements are automatic, and we implement intermediate layer for block transition randomly constructed. And therefore, the systems show sometimes a class 4 pattern, but sometimes a class 2, 3, or something like that. And we here we pick up only class 4 behavior, and as underlying lattice and estimate it with respect to complementarity and distributivity. There are some other hierarchical systems originated from rule 146, but we apply this idea automatically to all class 3 systems. And all class 3 systems matter as plotted in the plane, complementarity, distributivity as a red circle. And if implementing random middle intermediate layer transition on class 3 and zero matter leads to class 4 behavior, this transition is depicted by the diagram related to rule something like that. And the cross-plane ladders become more distributed and less complementary. This is a class 4 operations effect. Now, when we conclude some statement, implementing indefinite boundary on some file can result in a numeric system, varying exploration and exploitation. Implementing indefinite middle layer feature class 2 behavior on class 3 and third one can result in hierarchical class 4 serial output. It implements the notion of the matter since reductionism is not well defined because there's uncontrollable independence between two layers. Therefore, finally, two double rule we can see this conflict of the or discrepancy and the negotiation is essential for the evolution of autonomous system.